Hello, everyone, and welcome back. All right, this week I'm excited. This is actually one of my favorite sections to teach, and it's because this is the point at which we take what we've been learning about. We can now start to take some of this knowledge to understand what creates experience, what creates this sense that we are this unified self, that we have emotions, that we have thoughts, that we have this unique identity. The natural conclusion to everything we've just learned is that, well, if your psychology arises from these mechanical biological processes, then your sense of self, all of these highly personalized experiences, must also rise from that same psychology. So we're going to get into that, but I want to recap what we've learned so far and the most important points that I think that you should take away from our previous lessons. One, we learned in the first unit of this class that psychology is the scientific study of behavior and mental processes, and we focused on why it needs to be a science. I introduced various concepts like cognitive bias or heuristics, which are these systematic tendencies for us to act or think in a certain way that sometimes leads us to good judgment. It's very wise, for example, to follow authority bias, but at times it can lead us astray. And so we need some process that is external to us. The scientific method, a step by step procedure for attempting to control the influence of these biases on how we reason about the world around us, how we think the way the mind works. So it needs to be a science. Um, the other thing is that we learn what the nervous system is, what it does for us, what its function is, and that is it learns by creating and strengthening a network of neural connections. These neural connections, which then send signals up into the brain, as well as produce a response that the body can act on. And so, generally, we say that the nervous system's purpose is to process information. And we'll learn in a little bit more detail what I mean by that. That's a term that I think I've been throwing around. We'll really start to piece that apart, dig that apart, and what that means. But remember that a second function that I mentioned of your nervous system is that it is attempting to identify and record patterns. That is what learning is. When we talk about classical conditioning and operant conditioning, as well as memory, what your brain is doing is it's trying to take in features of the world around it and then make sense of it. Attempt to predict when, say, you put your hand on a hot stove, if that thing's going to hurt you, whether you should do that again. That's an important pattern to identify. So your nervous system does this for you. And there's a particular outcome to all of this that succinctly describes what this tendency is. So, this tendency to identify and record patterns, and that is patternicity. The tendency in this way, in some ways, you could think of this as another cognitive bias. We are more prone to try and find patterns than to believe that, say, patterns are not real, for example. We'll see evidence for that in a second. But it's the tendency to find meaningful patterns wherever we may be looking. Now, again, generally, this is a tendency that helps us. We want to identify patterns, but because of the way that our brain works, sometimes we can identify a pattern that is not real. And this is called apophenia. This is the tendency to mistakenly perceive connections and meaning between unrelated things. Let me give you some examples of this. This is an experience that you've probably had many times, maybe as you're just sitting somewhere, you're totally bored, and you start looking down at the ground, and maybe it's a tile or a marbled or a wooden floor, and there are little marks in it, and you might see something in the floor or in those marks. You might see a face. Well, faces are actually really easy for us to see. We have historically needed to identify facial features very quickly and very automatically. And so there is a built-in system within our brain that's meant to identify those patterns. So when you look, say, at the top left of this image here, and you see in the wood, what those are knots. So on the right side, you can see that those are knots in the wood. Those are formed when a tree takes damage, when it loses a limb, and then it creates this essentially scar tissue for plants. Well, when you cut into it, you get that left in the wood. And so sometimes you can get these odd patterns that almost look like faces, right? You see two eyes, you kind of see a nose coming down. You can see that dog's face in the wood. Now, there's not actually There's not actually a dog's face in there, but you perceive that there is. You can see that face and you can make sense of it. Just as much as you can make sense of the carabiner on the upper right end of the image here. So this is, of course, as you can all see, a metal carabiner connected to a piece of rope. The piece of rope extends down, and then there's a frayed end coming off on the left side. But that's probably not what you see when you first look at this image. You might look at this and say, "Wow, it kind of looks like this laughing face. This laughing face is sticking out its tongue, and it's flipping me off. It's giving me the bird." We perceive this is a pattern that is we've at least probably seen a couple of times, and so we're prone to see that pattern even in an inanimate object like a carabiner and some rope. Or if you look at the bottom, you look at this, you can almost see that these are like it's like a family. It's a very sad family, and they've all got really weird haircuts, and they're all depressed. Well, these are actually just toothbrushes lined up, but because we are prone to perceive faces, to see faces in what we're looking at, um, we see faces. So this is an example of apophenia, the tendency to perceive a pattern where there actually is none. So this is more apophenia applies to more than just visual images. So here's a nice little scenario I'd like you to imagine for yourself. So you experience on the following on a Monday, first day of the week. The alarm clock does not wake you up. You are now late for work. The cat has peed on the couch. The coffee maker is making strange noises and doesn't seem to be working. The kids are fighting with each other. It's raining. And on top of everything else, the car won't start. What do you conclude? Well, one or two of these minor irritants would seem insignificant and unmemorable, but once the list grows, it begins to take the shape of a plot of unseen forces, perhaps conspiring in a meaningful way against you. I think all of us have had this experience. You have a bad day, a day when things seem to go wrong all at once, and you assume that, there must be something happening that is causing all these unfortunate events to occur. Now, maybe that's true. Maybe they are all connected in some way. But the alternative possibility is that each of these is happening for a relatively independent reason. Or maybe there's an alternative explanation to it being a conspiracy or a plot. For example, let's say that you're just someone who typically does not take care of a lot of the stuff around your household. So you're not managing your car or the coffee maker, or you're not paying enough attention to your cats, which keep running around the apartment. Um, if you don't do these things, then of course they would break down. And the fact that they just happen to break down on one day is just chance. Now, is that a real pattern, or is that a fake one? Is that apophenia? That's the struggle. That's the tough part about having a nervous system. You can't always know. Here's another one that I think is very common. Belief in what are called angel numbers. So I'll just read this description here. Do you keep seeing the same number patterns often? They are angel numbers, and here's what they mean. People do this all the time. Actually, I think my most personal example of this is my brother had some angel number belief. So this is the idea that if you see certain numbers over and over again, or patterns of numbers over and over again, you start to say, wait a second, I'm seeing these numbers for a reason. I always see the number 1111 because in X, Y, or Z situation. What my brother did, not to call out my brother, but what my brother did is he ascribed meaning to when you look at a clock and you see on the clock that it reads 1111. And whenever he saw 1111, it was because he was currently pondering, currently thinking about, ruminating on, reflecting on something that had happened in his life, or some major event, or something that was deeply personal or emotional for him. And every time he was doing this, he'd look up and he'd see 1111. Well, he ascribed the pattern that, 1111 must have special meaning. Here's an alternative explanation. 11 o'clock at night is usually the time when people are winding down from the day. Maybe they're having trouble sleeping because they've got a lot on their mind. And then just so happens that at that time, when you are pondering about the day and what has happened to you throughout it, you look up at the clock to check what time it is. You're more likely to see 1111 because it's late at night. And that's when you think about this stuff. So is it an angel number, or is it coincidence based on what you typically do, your habits? Like I said, this is the problem. is we have a nervous system that's designed to detect patterns. Sometimes they are real, and sometimes they are not. How do we distinguish between them? Well, to address this question, I want to show you another video. I really like this one. This is a talk given by a psychologist named Michael Shermer, who has done a lot of research into conspiratorial thinking, false beliefs, superstition, etc. So I'll show this. It's about 17 minutes long or so, and then I'll continue after that. But enjoy.
So since I was here last, in 2006, we discovered that global climate change is turning out to be a pretty serious issue, so we covered that fairly extensively in Skeptic Magazine. We investigate all kinds of scientific and quasi-scientific controversies, but it turns out we don't really have to worry about any of this because the world's going to end in 2012. Another update, you will recall, because I introduced you guys to the Quadro Tracker. It's like a water dowsing device. It's just a hollow piece of plastic with an antenna that swivels around, and you walk around and it points to things. Like if you're looking for marijuana in students' lockers, it'll like point right to somebody. Oh, sorry. This particular one that was given to me finds golf balls, especially if you're at a golf course and you check under enough bushes. Well, under the category of what's the harm of silly stuff like this device, the ADE 651, was sold to the Iraqi government for $40,000 a piece. It's just like this one, completely worthless, in which it allegedly worked by electrostatic magnetic ion attraction, which translates to pseudoscientific baloney, would be the nice word, in which you string together a bunch of words that sound good, but it does absolutely nothing. In this case, allowing at trespass points, allowing people to go through because your little tracker device said they were okay, actually cost lives. So there is a danger to pseudoscience and believing in this sort of thing. So what I want to talk about today is belief. I want to believe, and you do too. And in fact, I think my thesis here is that belief is the natural state of things. It is the default option. We just believe. We believe all sorts of things. Belief is natural. Disbelief, skepticism, science is not natural. It's more difficult. It's uncomfortable to not believe things. So like Fox Mulder on X-Files, who wants to believe in UFOs, well, we all do. And the reason for that is because we have a belief engine in our brains. Essentially, we are pattern-seeking primates. We connect the dots. A is connected to B, B is connected to C, and sometimes A really is connected to B. And that's called association learning. We find patterns. We make those connections, whether it's Pavlov's dog here associating the sound of the bell with the food, and then he salivates to the sound of the bell, or whether it's a Skinnerian rat in which he's having an association between his behavior and a reward for it, and therefore he repeats the behavior. In fact, what Skinner discovered is that if you put a pigeon in a box like this and he has to press one of these two keys and he tries to figure out what the pattern is, and you give him a little reward in the hopper box there, if you just randomly assign rewards such that there is no pattern, they will figure out any kind of pattern, and whatever they were doing just before they got the reward, they repeat that particular pattern. Sometimes it was even spinning around twice counterclockwise, once clockwise, and peck the key twice. And that's called superstition, and that, I'm afraid, we will always have with us. I call this process patternicity, that is, the tendency to find meaningful patterns in both meaningful and meaningless noise. When we do this process, we make two types of errors. A type 1 error, or false positive, is believing a pattern is real when it's not. Our second type of error is a false negative. A type 2 error is not believing a pattern is real when it is. So let's do a thought experiment. You are a hominid 3 million years ago walking on the plains of Africa. Your name is Lucy, okay. And you hear a rustle in the grass. Is it a dangerous predator, or is it just the wind? Your next decision could be the most important one of your life. Well, if you think that the rustle in the grass is a dangerous predator and it turns out it's just the wind, you've made an error in cognition. You made a type 1 error, false positive. But no harm, you just move away, you're more cautious, you're more vigilant. On the other hand, if you believe that the rustle in the grass is just the wind and it turns out it's a dangerous predator, you're lunch. You've just won a Darwin Award. You've been taken out of the gene pool. Now, the problem here is that patternicity will occur whenever the cost of making a type 1 error is less than the cost of making a type 2 error. This is the only equation in the talk, by the way. We have a pattern detection problem. That is, assessing the difference between a type 1 and a type 2 error is highly problematic, especially in split-second life and death situations. So the default position is just believe all patterns are real. All rustles in the grass are dangerous predators and not just the wind. And so I think that we evolved. There was a natural selection for the propensity for our belief engines, our pattern-seeking brain processes to always find meaningful patterns and infuse them with these sort of predatory or intentional agencies that I'll come back to. So, for example, what do you see here? It's a horse head, that's right. It looks like a horse, must be a horse. That's a pattern. And is it really a horse, or is it more like a frog? See, our pattern detection device, which appears to be located in the anterior cingulate cortex, it's our little sort of detection device there, can be easily fooled, and this is the problem. For example, what do you see here? Yes, of course, it's a cow. Once I prime the brain, it's called cognitive priming. Once I prime the brain to see it, it pops back out again, even without the pattern that I've imposed on it. And what do you see here? Some people see a Dalmatian dog. Yes, there it is. And there's the prime. So when I go back, without the prime, your brain already has the model, so you can see it again. What do you see here? Planet Saturn. Yes, that's good. How about here? Just shout out anything you see. That's a good audience, Chris, because there's nothing in this. Well, allegedly, there's nothing. This is an experiment done by Jennifer Whitson at UT Austin on corporate environments and whether uncertain feelings of uncertainty and out of control makes people see illusory patterns. That is, almost everybody sees the planet Saturn. People that are put in a condition of feeling out of control are more likely to see something in this, which is allegedly patternless. In other words, the propensity to feel these or find these patterns goes up when there's a lack of control. For example, baseball players are notoriously superstitious when they're batting, but not so much when they're fielding. Because fielders are successful 90 to 95% of the time. The best batters fail 7 out of 10 times. So their superstitions, their patternicities are all associated with feelings of lack of control and so forth. What do you see in this particular one here, in this field? Anybody see a object there? There actually is something here, but it's degraded. While you're thinking about that, this was an experiment done by Susan Blackmore, a psychologist in England, who showed subjects this degraded image and then ran a correlation between their scores on an ESP test. How much did they believe in the paranormal, supernatural, angels, and so forth. And those who scored high on the ESP scale tended to not only see more patterns in the degraded images, but incorrect patterns. Here is what you show subjects. The fish, it's degraded 20%, 50%, and then the one I showed you, 70%. A similar experiment was done by another British psychologist named Peter Bruegger, who found significantly more patterns, meaningful patterns, were perceived on the right hemisphere via the left visual field than the left hemisphere. So if you present subjects the images such that it's going to end up on the right hemisphere instead of the left, then they're more likely to see patterns than if you put it on the left hemisphere. Our right hemisphere appears to be where a lot of this patternicity occurs. So what we're trying to do is bore into the brain to see where all this happens. Bruegger and his colleague Christine Moore gave subjects L-DOPA. L-DOPA is a drug, as you know, given for treating Parkinson's disease, which is related to a decrease in dopamine. L-DOPA increases dopamine. An increase in dopamine caused subjects to see more patterns than those that did not receive the dopamine. So dopamine appears to be the drug associated with patternicity. In fact, neuroleptic drugs that are used to eliminate psychotic behavior, things like paranoia, delusions, and hallucinations, these are paternicities. They're incorrect patterns. They're false positives. They're type 1 errors. And if you give them drugs that are dopamine antagonists, they go away. That is, you decrease the amount of dopamine, and their tendency to see patterns like that decreases. On the other hand, amphetamines and cocaine are dopamine agonists. They increase the amount of dopamine. So you're more likely to feel in a euphoric state, creativity, find more patterns. In fact, I saw Robin Williams recently talk about how he thought he was much funnier when he was doing cocaine, when he had that issue, than now. So perhaps more dopamine is related to more creativity. Dopamine, I think, changes our signal-to-noise ratio. That is, how accurate we are in finding patterns. If it's too low, you're more likely to make too many type 2 errors. You miss the real patterns. You don't want to be too skeptical. If you're too skeptical, you miss the really interesting good ideas. Just right, you're creative, and yet you don't fall for too much baloney. Too high, and maybe you see patterns everywhere. Every time somebody looks at you, you think people are staring at you, you think people are talking about you, and if you go too far on that, that's just simply labeled as madness. It's a distinction perhaps we might make between two Nobel laureates, Richard Feynman and John Nash. One sees maybe just the right number of patterns to win a Nobel Prize, the other one also, but maybe too many patterns, and we then call that schizophrenia. So the signal-to-noise ratio then presents us with a pattern detection problem. And of course, you all know exactly what this is, right? And what pattern do you see here? Again, I'm putting your anterior cingulate cortex to the test here, causing you conflicting pattern detections. You know, of course, this is via uno. Shoes. These are sandals. Pretty sexy feet, I must say. Maybe a little photoshopped. And of course, the ambiguous figures that seem to flip-flop back and forth. Turns out what you're thinking about a lot influences what you tend to see. And you see the lamp here, I know, because we have lights on here. Of course, thanks to the environmentalist movement, we're all sensitive to the plight of marine mammals. So what you see in this particular ambiguous figure is, of course, the dolphins, right? You see a dolphin here, and there's a dolphin, and there's a dolphin. This is that's a dolphin tail there, guys. If we can give you conflicting data, again, your ACC is going to be going into hyperdrive. If you look down here, it's fine. If you look up here, then you get conflicting data, and then we have to flip the image for you to see that it's a setup. The impossible crate illusion, it's easy to fool the brain in 2D. So you say, oh, come on, Shermer, anybody can do that in a Psych 101 text with an illusion like that. Well, here's the late, great Jerry Andrus's impossible crate illusion in 3D, in which Jerry is standing inside the impossible crate. And he was kind enough to post this and give us the reveal. Of course, camera angle is everything. The photographer is over there, and this board appears to overlap with this one, and this one with that one, and so on. But even when I take it away, the illusion is so powerful because of how our brains are wired to find those certain kinds of patterns. This is a fairly new one that throws us off because of the conflicting patterns of comparing this angle with that angle. In fact, it's the exact same picture side by side. So what you're doing is comparing that angle instead of with this one, but with that one, and so your brain is fooled. Yet again, your pattern detection devices are fooled. Faces are easy to see because we have an additional evolved facial recognition software in our temporal lobes. Here's some faces on the side of a rock. I'm actually not even sure if this might be Photoshop, but anyway, the point is still made. Which one of these looks odd to you? And a quick reaction, which one looks odd? The one on the left. Okay, I'll rotate it so it'll be the one on the right, and you are correct. Fairly famous illusion that was first done with Margaret Thatcher. Now they trade up to politicians every time. Well, why is this happening? Well, we know exactly where it happens, in the temporal lobe, right across, sort of above your ear there, in a little structure called the fusiform gyrus. And there's two types of cells that do this, that record facial features, either globally or specifically these large rapid-firing cells. First, look at the general face, so you recognize Obama immediately. And then you notice something quite a little bit odd about the eyes and the mouth, especially when they're upside down. You're engaging that general facial recognition software there. Now, I said back in our little thought experiment, you're a hominid walking on the plains of Africa. Is it just the wind or a dangerous predator? What's the difference between those? Well, a wind is inanimate. A dangerous predator is an intentional agent. And I call this process agenticity. That is the tendency to infuse patterns with meaning, intention, and agency, often invisible beings from the top down. This is an idea that we got from a fellow tedster here, Dan Dennett, who talked about taking the intentional stance. So it's a type of that expanded to explain, I think, a lot of different things. Souls, spirits, ghosts, gods, demons, angels, aliens, intelligent designers, government conspiracists, and all manner of invisible agents with power and intention are believed to haunt our world and control our lives. I think it's the basis of animism and polytheism and monotheism. It's the belief that aliens are somehow more advanced than us, more moral than us, and the narratives always are that they're coming here to save us and rescue us from on high. The intelligent designer is always portrayed as this super intelligent moral being that comes down to design life. Even the idea that government can rescue us, that's no longer the wave of the future, but that is, I think, a type of agenticity. The projecting somebody up there, big and powerful, will come rescue us. And this is also, I think, the basis of conspiracy theories. There's somebody hiding behind there, pulling the strings, whether it's the Illuminati or the Bilderbergers. But this is a pattern detection problem, isn't it? Some patterns are real and some are not. Was JFK assassinated by a conspiracy or by a lone assassin? Well, if you go there, there's people there on any given day, like when I went there here, showing me where the different shooters were. My favorite one was he was in the manhole, and he popped out at the last second and took that shot. But of course, Lincoln was assassinated by a conspiracy, so we can't just uniformly dismiss all patterns like that, because let's face it, some patterns are real. Some conspiracies really are true. Explains a lot, maybe. And 9/11 as a conspiracy theory. It is a conspiracy. We did a whole issue on it. 19 members of Al-Qaeda plotting to fly planes into buildings constitutes a conspiracy, but that's not what the 9/11 truthers think. They think it was an inside job by the Bush administration. Well, that's a whole nother lecture, but you know how we know that 9/11 was not orchestrated by the Bush administration? Because it worked. So we are natural-born dualists. Our agenticity process comes from the fact that we can enjoy movies like these because we can imagine an essence continuing on. We know that if you stimulate the temporal lobe, you can produce a feeling of out-of-body experiences, near-death experiences, which you can do by just touching an electrode to the temporal lobe there. Or you can do it through loss of consciousness by accelerating in a centrifuge. You get a hypoxia or a lower oxygen, and the brain then senses that there's an out-of-body experience. You can use, which I did, went up and did Michael Persinger's God helmet that bombards your temporal lobes with electromagnetic waves, and you get a sense of out-of-body experience. So I'm going to end here with a short video clip that sort of brings all this together. It's just a minute and a half. It ties together all this into the power of expectation and the power of belief. Go ahead and roll it.
Except that I feel that that video doesn't do a very good job of summarizing his point, so I'm going to exclude it. But of course, if you want to watch it yourself, you can find this video. Links at the bottom. But I think that this video is a fantastic transition between what we've been learning and where we're going. Because the argument here is that our brains are designed to detect patterns, and what we've learned is that the machinery exists for us to be able to detect and learn patterns. So how that transitions into the next part of our class is we're going to start going over what's called sensation and perception. This refers to two different processes that together describe how our brain processes information, how it identifies those patterns. Sensation is going to refer to how the brain receives information. So we've already talked a little bit about this. You've learned about dendrites, which are those little spindly projections that come off of the neuron's cell body, that these presumably take in information. But it's a little bit more complicated than that, because for our neurons to even receive a signal in the first place, the information in the outside world, such as light and sound and flavor and smell and touch, all needs to be translated into a language that our nervous system can understand. That is, our nervous system can't automatically just understand what a photon is, which is the particle that makes up light, or what certain vibrations within the air, which are what's responsible for sound, determines what that sound's experience is like. So what we need to do is we need what are called sensory organs, or full of what are called sensory receptors that are responsible for translating those physical elements into the electricity that our nervous system can understand and transmit and make sense of. So we first need that process. How do we take in information? Then, of course, once it's in the nervous system, what does your brain do with it? How does it actually make sense and identify patterns within it? And that'll be perception. So we'll start out with going over sensation, we'll go into perception, and then we'll try to put this all together and see if it makes sense within this context of how is your brain identifying patterns, and when can that pattern detection go wrong? When might you experience apophenia? All right, so if we're going to talk about this, I need to introduce you to a few basic concepts within the study of sensation. First, we need to know how information enters the brain, and I've already mentioned this through what are called sensory receptors. These are any receptor, a specialized structure within your body, a specialized set of cells, that is, its sole purpose is to convert sources of energy into an action potential. So we already know what an action potential is. That is that electrical charge that is generated by the neuron when sodium and potassium switch places and you get a depolarization and a repolarization and then the refractory period back to normal. That's an action potential. So receptors are going to convert energy sources, again, light, sound, the chemicals within food, for example, into these electrical signals. Now, each of our senses is associated with a different energy signature. So when I say energy, I don't mean, some mythical, energy that surrounds us all kind of thing. I literally mean within physics, these are considered types of energy. So we have vision, which of course is light made up of photons. We'll learn about these properties. Hearing, when you hear something, sound is the consequence of vibration. So when you hear something, if I were to say, knock my hand against the desk, the reason that you can hear that sound is that my hand striking the desk causes vibration, which then travels through the air, enters my microphone, gets played through your speaker, all through vibrations. That's how speakers work. They create vibrations to mimic a certain sound. Those vibrations then get sent through the air wherever you are. Perhaps if you're wearing headphones, almost a direct link between the speaker and your ear, into your head, and then through the eardrum. We'll learn all about this, but ultimately into your head, recognized by each of the parts of the ear and the sensory organ, and transforms the physical vibration into an experience of what sound is. That's a lot to say. We'll go through these processes. Don't worry if you didn't catch all that. With smell and taste, the energy that is being detected here is actually the energy contained between chemical bonds. Now, if you've had, again, basic physics, chemistry, you probably learned about atoms, elements, that can come together to form bonds with one another and with bonds with other elements to create compounds. When you form those bonds, what you're doing is you're storing a certain amount of energy between them. When you eat food, what you're doing is you're taking prepackaged energy that might come in this form of sugar, protein, fats, etc., putting it within your mouth starts to digest it. And as the food is being digested, the enzymes, the proteins within your digestive tract start to break down those chemical bonds, and the energy that gets released by that breaking down is then detected by sensory receptors within your tongue. What are the sensory receptors within your tongue? Taste buds, which, spoiler alert, are not the small little bumps on your tongue. They're actually these particular organs that are these particular receptors that are in between those bumps. But that's what it is. You are detecting the chemical properties of the food that you are tasting. Same with smell. Smell is actually, you are detecting the chemicals within whatever you are smelling. We have specialized hairs within our nose that are responsible for detecting those chemical properties. And then touch is a lot of different things. We have temperature, which of course is the ability to detect whether something's relatively warmer, relatively colder, which we know is associated with a physical property of certain atoms. So when something is relatively warmer, we know that atoms tend to be more spread apart. Warmth is associated with more energy existing between the atoms. Therefore, they tend to be spread. Whereas when something's cold, there's relatively less energy between those atoms, and so they tend to be clustered together and they vibrate somewhat slowly and not very far from their starting position. So when you detect temperature, it's because you have sensory receptors that are specialized for detecting the amount of energy contained between atoms in a particular substance. So if you have a nice cold bottle of water, the amount of energy contained within this water is relatively lower, and I'm detecting that. Versus if I drink hot tea, there's more energy between the bonds of the water that make up that tea, and therefore it tastes hot, or it feels hot. We have sensory receptors for detecting pressure, which tend to be somewhat deeper within the skin. And we can also detect texture, which is really, if you think about it, your ability to detect how irregular a surface is. So when something is smooth, it means that that surface has a fairly consistent, it's quite consistent in the way that it's constructed. Versus if something is relatively rougher, like sandpaper, that means that there's more variability, there's more what are called perturbations within that material. And so you're detecting how irregular that surface tends to be. We'll also go into what are called somesthetic senses and vestibular sense, that is a sense of where your body is within space, as well as your sense of balance. Each of these is your body's attempt to detect energy signatures that it needs to make informed decisions, to make a judgment about what's going on in the world around it, and then, of course, create an experience from that. So, a couple more important basic terminology bits that you need before I set you loose on some of the other videos in this section. I need to describe what's called the just noticeable difference. This is defined as the amount of change in an energy source. Again, that light, sound vibrations, chemical properties. The amount of change in that energy that is required for you to be able to perceive or see or taste or hear that change. So how much does an energy source need to change for you to be able to detect it? I'll put you through a slight little exercise here. Looking at these circles, quickest judgment, are these circles the same color or are they different? You probably say, of course, they're the same. Okay, that's an easy one. How about these? Okay, they're different. That's pretty clear. All right, are these circles the same or different? Now let me compare that to this. Are these circles the same or different? Okay, just gut reaction. How about, are these circles the same or different? What about these circles? I am actually changing the slide here, I promise. But if you go back and forth, I'm going to very quickly go through these slides again. Pay attention to how much these actually change compared to perhaps what you saw the first time. So I'm just going to filter through these. And if you look closely, depending on how good your resolution is and whether you're viewing on a good device or not, you can see that the color is actually changing, right? It's at least getting slightly brighter. The reason I know that these colors are different is because when I made these images, I went into Paint, and they have that little that device where you can, or that option where you can put a certain color, then use the eyedropper to sample it, and then change the lightness of it just ever so slightly using that slider. That's what I did here. So these are, not that one, that one's clearly different, but these are here technically different colors. They're different in brightness. But the first time I showed them to you, you probably went, yeah, that's the same. It looks the same. Like, okay, what's the point? This is the point. Those were changing, but the change in the energy source, that is light, and we'll learn that the color is associated with wavelength. The wavelength change, the change in the wavelength of the light was not great enough for you to detect color. That's the just noticeable difference. The amount of change required to perceive that change. So things can change and you might not be aware of it. Another term you need to be familiar with, something called absolute threshold. This is the lowest level of stimulation required to perceive a stimulus. That is the minimum amount of a certain type of energy that you need to be able to detect that it's even there. The idea is if the stimulation does not surpass this threshold, you will not detect it. So let me give you an example here. If I hit the table with my fist here, you can hear that. And it's because the amount of vibration that's coming off of this table is substantial enough that you can, as it goes through the speaker, or it goes through the microphone, exits through your speaker, you can actually detect it. Now I'm going to do that a little bit more softly. And because my microphone is awesome, you can probably hear that. So now it's less intense, but it's still intense enough for you to detect it. Now compared to maybe something like this, let's see if I can do this. You might be able to still hear that. But what I'm doing is I am hitting my table right now. I'm creating vibrations. However, they may not be intense enough that when they travel through the air and they make it to my microphone, they've already lost some of that energy in transit. And so now when it hits your ear, there's not enough of it for you to detect that it's there. If I were to go into a soundboard and actually measure how much sound is being picked up, I'm probably detecting something with my mic, but it may not be enough for a person to be able to detect it because our sensory receptors, the amount of energy that is being processed by the sensory receptors is not substantial enough to detect it. Now, does this remind you of anything? If you think back to chapter 3, chapter on biology, when we were talking about action potentials, generating that electrical charge, depolarization, repolarization, there was a certain point where as a cell was being stimulated and it was becoming more positively charged on the inside, there was a point that it had to reach, a certain voltage that it needed to reach for the cell to even generate an action potential in the first place. That is, at rest, the inside was negative 70 millivolts, and the exact number is that it had to reach negative 55. It had to become sufficiently positive enough for depolarization to occur. If it never reached that, depolarization never happened, you didn't get a signal, the neuron was not activated. That is the absolute threshold. It's how much stimulation needs to be detected for that neuron to send any signal whatsoever. If the stimulation is not sufficient, then the neuron just doesn't send the signal, and so the information does not get transmitted. That's absolute threshold. There's something called subliminal perception. This is, I think, something that has a lot of incorrect popular belief surrounding it. So subliminal perception is a thing. It's when you detect stimulation even when you are not consciously aware of it. Now, I think the best example of this is something that we just recently talked about, the cocktail party effect. Recall that this is, you're at a party, you're very focused on a particular conversation that you're having, and then you're not listening, you just hear the mumbo jumbo happening around you, you're not sure what it is, and then someone says your name. In that moment, your brain goes, oh, my name was said, and you start paying attention to whoever said your name. In that moment, your brain is detecting that sound. It's monitoring the conversations that are happening around it. But it's not explicitly paying attention to it, or it's not aware that it's paying attention to that sound until something really important is said, until something is relevant enough for the brain to respond to it. That's subliminal perception. So you're detecting stimulation, but you may not be consciously aware that it's happening. Now, what's not true about subliminal perception is that there are some who use what's called, you may have heard of something called subliminal advertising. And that is, this was a technique that was tested out, and I want to say back in the 50s and 60s, where what they would do is advertisers, marketers would attempt to put in very short, very brief, hard to detect advertisements for certain products in movies, shows, etc. So that is, you're just watching a TV show and then suddenly boom, something flashes real quick. You barely know it's there, but the logic was that, oh, just by seeing this say Coca-Cola ad for a fraction of a second would make you go, oh, I really want Coca-Cola now for some reason. I'm not sure why, but I just want to go. It doesn't work that way. That actually doesn't. So people who are subjected to that subliminal advertisement are not more likely to purchase the product than those who are not exposed to the subliminal advertising. So in terms of using it as a technique for convincing people to do something, not so much. But does it simply exist? Yes. That's subliminal perception. The last two concepts that we need to go over are related to one another. And as you're taking the exam for this chapter, I'm going to warn you, I will ask about these two, and you'll need to know the subtle difference between them. They both refer to something that the brain does when it is receiving unchanging information. Habituation is when you pay less attention to unchanging information. And compared to sensory adaptation, this is considered more psychological in that you are allocating less of your selective attention to something. You're simply paying attention to it less. A good example of habituation, let's say that you are in college or you're taking a class and you have a professor. And this professor, the way that they lecture is that they tend to be very monotone. This is the only tone they have. So as they're explaining their lessons, they're talking about habituation and sensory adaptation. There's absolutely no inflection in their voice. They seem to just keep rambling, and this is all you're getting over and over again. As you begin to listen to this continuously, you start to get bored because it's just the same voice, the same thing. There's no change whatsoever, and so you're going to stop paying attention to me after a while because I just sound the same. You can't really distinguish between the different, you can't detect those subtle differences. See, that's hard for me to do. And it's because I find it boring. If you've ever had a teacher who simply talks like that, they seem to lecture continuously, it's hard to pay attention. It's hard to keep focus. This is why I inflect so much. Those of you who have not figured it out, this is not how I talk to people in my day-to-day life. This is not me. This is my performance voice. I tend to go really high. I say something, I'm excited, and then I pause, and then I change the tone of my voice. I realize that if I do not do that, you're going to stop paying attention to me. I don't want that. So I am intentionally trying to prevent you from going through habituation. I don't want you to stop paying attention to me just because the sound of my voice is unchanging. All right, that's habituation. Compare that to sensory adaptation, which is considered more biological. So that rather than your brain, you not allocating selective attention, this is when the sensory receptors physically themselves become less responsive. That is, if you bombard sensory receptors with the same information over and over and over and over again, they may simply stop responding to it. A good example of this is when you're eating food, what your favorite food. Let's say you go out to a restaurant and you order your absolute, just the tastiest thing that you love. For me, because I'm very basic, I love Alfredo, pasta Alfredo. Just give me that nice cheesy, creamy, milky sauce over pasta. I go nuts for it. When I get it, I usually take a bite and I go, oh yeah, that tastes so good. And then I take a second bite and I'm like, yeah, I'm ready for that goodness again. But it's never quite as good. It's slightly less good the second bite. And then by the third bite and the fourth bite and the fifth bite, you're basically just putting that stuff in your mouth and not really enjoying it like you did when you first tasted it. When food seems to lose some of its flavor or lose some of its novelty because you've already recently just tasted it, it's because the sensory receptors, those taste buds, are responding less to the chemicals within that food. This is why it's a good idea when you're eating a meal is to do a little bit of palate cleansing. So you taste something, maybe drink a little bit of water, or maybe you then, after you've eaten that, you taste something else on your plate, and then you drink a little bit of water, and you try to vary things up so that every time you eat something, Your sensory receptors are not fatigued. They are not exhausted. They are not overused. That's why people do that, if you do that. Some of us, like me, I just scarf down that pasta because I just don't have any patience otherwise. So the sensory receptors are generating fewer action potentials, fewer of those electrical charges. Now there's an exception to this. All senses undergo sensory adaptation, except for vision. Imagine what would happen if vision underwent sensory adaptation. That is, the visual information, those photons, are unchanging. You're seeing the same image again and again and again. If vision underwent sensory adaptation, as you're looking at something, say you're just focusing on a piece of paper, words written on a piece of paper. As you're looking at that piece of paper and you just are looking at the same word continuously, that word would disappear. You'd stop seeing it because your eyes would, because the sensory receptors, the photoreceptors in your eyes would become less responsive to that unchanging information. So why doesn't it? Well, your body has accounted for this. Your eyes undergo something called microsaccades. Next time you're getting intimate with someone, so next time you're really up close to someone and you can look into their eyes for a prolonged period of time up close, look at their pupils and you'll actually notice that they're vibrating slightly back and forth. There's a movement to them. Those are called microsaccades. The logic is, if your eyes are constantly moving back and forth, just ever so slightly, what that's doing is it's refreshing the image of whatever you're looking at on the retina of your eye. So it's refreshing that image so that your sensory receptors do not become fatigued. They keep responding to what they're looking at. So your eyes essentially artificially change the information so that it doesn't treat it as unchanged information. All right, that's habituation, sensory adaptation. Know the difference between those, as well as microsaccades. All right, so this week we're going to take a tour of the different sensory organs. So we're going to have classes on the visual sensory system, including the eyes and how the eyes do their job. We'll talk about auditory sensation, the structure of the inside of the ear, which is much more complicated than perhaps you realize. We'll talk about chemical organs, which are the nose and the tongue for detecting chemical properties of matter. And then the somesthetic organs, skin, and touch, temperature, pressure, as well as I mentioned the kinesthetic sense, where your body is within space at a given time, as well as your vestibular sense, which is your sense of balance and whether your body's likely to tip over or not. So we'll get into that. Here's my reminder, as always, do that research participation, 2 in-lab credits, 2 online credits. If you have any questions about that, please do let me know. Thanks, everybody.